Okay, so the good news is from now on we're going to talk about limits in a sort of concrete way. We're not going to talk about them abstractly. We're going to start actually finding these things and going with them. So first block was a lot of conceptual thinking about it. So let's talk about algebra, how we do these things without the graphing calculator. Now, there's some preliminary stuff. Let's say we have two functions. We know the limits for both, and they're given to us, or we figured them out. The limit for the first function is L. The limit for the second function is M. So there are some things that we should get out as preliminaries. The good news is the sum of two limits is the limit of the sums. It is as you would expect it. You can just add them together. Same thing with the difference rule. It's possible that you go the limit as f of x minus g of x will be the same thing as just taking L minus M. Okay. The product of limits is also safe. Okay? The limit as x goes to c here would be f of x times g of x will be equal to L times M. And any constant would also be, we could go some constant, let's choose the letter K. It would just be K times L. So far everything behaves the way you would expect it to in limits. There are times when we get further on, it'll make sense why, but there are times when these things won't work for some of our applications, but for limits they will. If we had the limit as x goes to c of f of x over g of x, then that would be the same thing as L over M. And if we had the limit as x goes to c of f of x to some exponent, then that's the same thing as taking the exponent to the limit L. So good news is algebra with limits works the same way as it normally does for you, so there's no real extra rules to learn. So let's take a look here at how we can, sorry, I'm just going to have to apologize in advance. We are going to be moving faster this time around because of that fire drill we missed. But I promise this one a little easier to think about. So limit laws can be combined into an expression like a polynomial. So a polynomial has coefficients and exponents. So you can apply those rules to a polynomial, and that's why they work out so easily, is just substituting it. Okay? This is what we're going to be talking about now, the interesting limits. This is an incomplete list. There are more interesting limits, but we're going to look at those later. For now, these are our interesting cases. When we run into a 0 over 0 or infinity divided by infinity, that's where interesting things happen. That's where we'll have to do more than just say, oh, the limit doesn't exist, or oh, I can just get it directly when I substitute in. So let me show you what I mean. In this first example here, if I substitute it in, I would get 1 plus 1 minus 2 over 1 minus 1, which is 0 divided by 0. So that's one of the interesting limits. Algebraically, since you're not looking at your calculator, that should make you say, I have to do a little more work here. I can't just go, oh, divided by 0, don't have to do anything. This is one of the interesting ones. Here's how we do it algebraically without a graph. We're going to factor this. So instead, I'm going to think about this as the limit as x goes to 1 of x, let's see here, plus 2 times x minus 1 over the limit, over x times x minus 1. Then what happens, you'll notice, is these pieces end up disappearing. Okay? And it's equal to the limit as x goes to 1 of x plus 2 over x. Now there's no more division by 0. This would just be substituted in as 1 plus 2 over 1, which is 3. So that's what we're going to be trying to do algebraically, is look for a way to remove the problem. In this case, the problem was because 1 would cause a division by 0 in the denominator. I figured out a way right here to get that division by 0 removed. Okay? So that's what we're looking for algebraically, is an equivalent expression that will remove the problem. Okay, I'll give you just a second. Okay, so here's what we've got happening. The picture of those two graphs. The one on the left was the original one that we were working with, and it would have a hole right there because it's not defined at x equals 1. It also has an asymptote at x equals 0, the other spot where there's a problem. Okay? This one problem, we actually ended up removing it by doing this here, which is why we could evaluate it this time. Meaning, as I got super, super close, it gives me the value where normally it's not defined. Okay, so you can see from the picture that they're actually almost the same thing. So, your turn. See if you can figure out algebraically these limits exist. See if you can do this and work out how to remove the problem with these. Okay, so hopefully that was some time to get organized. This would be the limit as x goes to 5 of x minus 5 over x plus 5 times x minus 5. So now you can see what used to be the problem is going to end up being removed. And I have a graph which will be 1 over x plus 5. So that means the limit would equal 1/10 if I was to look at this in my calculator. As well here, if I put in a -2, then I'm going to have 4 minus 4 on the top, then -8 plus 8 on the bottom. So it's an interesting one, 0 over 0. So the work I'm going to do this time is I'm going to factor out. So this will be the limit as x goes to -2 of -2 x plus 2 over x squared times x plus 2. And that problem is now gone. So this will be the limit as x goes to -2 of -2 over x squared, -2 over 4. So if I was to look at this on the graph, I would see that the graph is approaching a half. Okay, so hands up if you were able to algebraically do those limits. Hands up if you like it better than epsilon delta. Okay, figured. All right, so there's another strategy that you might have forgotten. Called rationalizing. So do you remember this pattern? If you multiply those together, do you remember what that is? Yeah, the difference of squared. So it'll be a squared minus b squared. Okay. So just to quickly show you then rationalizing stuff. In this first example, if I was to apply that pattern, it would be 5 minus 4, which is 1. And in this one, if I put some algebraic symbols like x's, it would be x plus 4 minus 4. So this would turn out to be just x. So that's what we're going to shoot for here, is simplifying these things by rationalizing. I will do the first one for you, and then I've got a couple for you to try. So in this example, if I tried it, it would be root 9 minus 3 over 9 minus 9. So that's 0 over 0. So again, this is an interesting situation that we need to pay some more attention to. So I'm going to figure out how I could simplify this. Now, it is possible to do it by factoring, just harder. So when you see the square root, one other thing you can try is you can try rationalizing. So I'm going to multiply this by root x plus 3 on the top and the bottom. Then what I'm going to have is the limit as x goes to 9. The top will become x minus 9. And the bottom doesn't share that pattern, so I don't need to worry about expanding it there. I'm just going to keep it factored. And you'll notice that now the problem here, dividing by 0, has been removed. And I will have the limit as x goes to 9 of 1 over root x plus 3, which is 1 over root 9 plus 3, which is 1/6. So you try rationalizing the other two examples. See if you can use that strategy for x minus 1 over root x plus 3 minus 2, and the other one there. Okay, so I'll try to catch up to to u here. So the pattern I'm going to try on this one is root x plus 3 minus 2 over root x plus 3 minus 2. Plus 2, thank you, sorry. So again, the top does not share the pattern, so there's no need to expand it. I'm hoping that something's going to eliminate here. X plus 3. So it's better to be factored since I'm looking to eliminate stuff. Then this will become x plus 3 minus 4. And that's the limit as x goes to 1 of x minus 1 root x plus 3 plus 2. And on the bottom I have the x minus 1. So those would disappear, and I'm left with the limit as x goes to 1 of root x plus 3 plus 2. And that I can do by direct substitution. Root 4 plus 2. So it would actually just have the value 4 after I've simplified it. In the next example, this time I'm going to multiply by 2 plus root x. And again, I wouldn't expand the top because I don't see a pattern there. So I will leave it as 4x minus x squared times 2 plus root x. Okay. And then on the bottom, I'm going to have 4 minus x. So this is a little bit, there's one more step there. Does anybody see how I can get rid of that problem? Yeah, if I factor the top part, the limit as x goes to 4, I take an x out. Then that problem now disappears. Okay. So I can put down my simplified form. And that will be 4 times, sorry, that's not a 3 there, that's an x. Times 2 plus root 4. So that's 4 times 4. So this would take on the value 16. Okay. So I'll give you a minute in case you needed to. Does anybody need more time on that one? Just a second? Okay, I'll leave it up there just for a minute.